All right, ladies and gentlemen, I'm hoping this will be a relatively quick video. And what I mean by that is it'll allow me to see how much we've retained. This is not going to be that bad of a video, but it is going to have some languaging to it. And I do want to make sure that we have a firm understanding. So before we jump on in, let's make sure we understand what you're going to need for this video. You should have watched the last three. They all talk about anti-differentiation and how it really just started off as a conversation as undoing the derivative. So that's why it was anti-differentiation. But then after some work and we looked at linear motion and the relationship between position, velocity, and acceleration, we started to realize that there's a bigger story and that it gives you area underneath the curve. But sometimes to get the perfect area underneath the curve, you're going to have to combine some calculus, taking the limit as the little bases of the little rectangles underneath the Riemann sum. They get super duper small, and that gives us the integral. Okay, so we're going to do a quick cover up. I'm going to go through the whole story, and then I'm going to introduce to you the part 2 of the fundamental theorem of calculus, and it's a really easy concept. So let's jump in. Okay, and this is basically what it says. It says that if there's a function known as the antiderivative, and if you can find it, antiderivative of that, then you know that when you antiderive a function, it is literally the net change. Now, you're probably saying to yourself, how is this different than what we've been doing on the last 3 videos? Well, let me show you, okay? So what this is saying is this, is if from some spot A to some spot X, okay, and we're on the function f, so this is f, and these are t values technically, okay? They're saying this, that if I want to find the integral from a to b, which is effectively the a to x, if this thing happens, so and remember, x is changing, so these are the numbers we're plugging in. So basically what they're telling you is from starting point, we can figure out the area of any x value on that function, right? So we could be finding different areas. So what they're telling you is that doing the integral gives you the area from point A to point B. If that does happen, then this idea of net change being the integral can then happen. So that's the big idea behind it. So is it really a big thing that we found? Not really, okay? All we found is that it just reinforced the idea that when we integrate, the net changes a point A from a point B. That makes good sense, right? When we start looking at the area underneath that curve, which is the net change. All right, so here we go, moving on. So the big question is when we start talking about the net change, i.e. the integral, what is the difference between a definite versus an indefinite integral? And that's what I think a lot of people just do not get. A definite integral is a guy that's defined. So let's say from 0 to 2 of x squared dx versus a guy that does not have any bounds. Well, what's the difference? Well, if we were to calculate this guy, I'm not going to go through the calculations with you. You're going to get x squared plus c. That's not a c. My goodness. C evaluated from 0 to 2. This side, you get x squared plus c. So you're like saying, Resh, well, that's the same things. Well, no, because a definite integral, you can actually go through the actual idea of plugging in those values, and then the c's will always drop out, no matter what. So when we start talking about definite integrals, you'll see people stop writing the c, because the c's always drop out no matter what. We can cut off the middleman. So that is the major difference between a definite and indefinite integral. And again, we talked about that the anti-differentiation or indefinite integral, this is some videos back, probably 3 videos back, we talked about how it's just a net change. So please go back and look at that if it's not totally clear with you. All right, so the question comes in is you got to know what an integral can do for you, okay? So it's not just about, and this is basically a warning, okay? Learning about them is not just about calculating a number, which is often the big thing, okay? Remember, Learning an integral is a sum, right? A sum of those little bits and slices is how we get the perfect areas. That's huge. Learning that when we integrate from an A to a B, we're getting the area underneath that curve. That's huge. And then finally, if you know that when you can, that integrating, it should be little f, not big F, can always be approximated if you don't know what to do, right? And what do you mean approximated? By doing a Riemann sum. Can be approximated with a Riemann sum, and that would be like a LN kind of situation. How many rectangles? Okay, so if you to integrate, you're just adding it all together, right? The smallest slices. But if you don't know how to get those slices, then the best you could do is just slice it up because you're a human and add it up and try to get as good as possible. That's basically it, guys. All right. Next video, we're gonna nail a whole bunch of examples and go through it. It's gonna be really quick. This part of the semester is fun because we get through stuff very quickly and it makes perfect sense. So let me know, and I'll see you guys on the next video. Bye.